Okay, let's dive into this. Welcome to This Explainer, where today we are unraveling what I like to call the ultimate astronomical detective story. We're looking at our solar system and asking a very simple yet totally baffling question. Why do we practically ignore our closest neighbor, Mercury? I mean, it's right there. Yet it remains one of the absolute most enigmatic, unvisited celestial bodies in our entire cosmic backyard. And the statistical discrepancy we're dealing with here is honestly kind of shocking. Humanity has sent 30 missions to Mars. We've sent 22 to Venus. We've even managed to send 3 whole missions all the way out to distant freezing Pluto. But Mercury, despite being physically closer to us at times than Mars or Venus, it has seen almost 0 dedicated missions. So how does a planet sitting right under our noses get completely bypassed by decades of space exploration? Section 1. Mariner 10's Tragic Fate. To understand why, we really have to look at NASA's Mariner 10. This was the very first probe brave enough to attempt this incredibly treacherous journey. And the craziest part? It had to do the whole thing without a massive supply of traditional fuel, relying almost entirely on the invisible hands of planetary gravity to pull it along. Launching in November 1973 from Florida, the scientists were basically holding their breath. But by March 1974, it did something totally revolutionary. It used Venus for a gravity assist. It practically surfed the gravitational wave of Venus to slingshot itself toward Mercury, gaining some absolutely crucial speed. And this precise gravitational slingshot technique is exactly what we use today to send probes out into interstellar space. But, well, ultimately the triumph here was incredibly short-lived. Under normal circumstances, a successful planetary probe will snap upwards of 25,000 photos of its target to beam back to Earth. Mariner 10? It only managed to capture 2,700. Now, don't get me wrong, those included some of the very first high-definition photos of Venus, which was a huge win for us. But long before it could complete its primary mapping mission of Mercury, its fuel reserves for course correction just ran completely dry. And its demise was absolutely dramatic. Because it couldn't correct its course, it was constantly getting deflected by the intense solar radiation of the sun. Eventually, it got pulled directly into Mercury's gravitational grip. It plummeted right into the planet's surface at roughly 5 times the speed of sound. Actually, let me put that into perspective. The kinetic energy released by this tiny probe crashing was utterly catastrophic, equivalent to the energy required to completely vaporize the entire Great Pyramids of Giza. Just a spectacular, violent end to a historic mission. Let's move to Section 2 and see how this builds. The Sun's Gravity Trap. Now, what's really interesting about this slide is that it wasn't just bad luck that doomed Mariner 10. No, it's a fundamental physics problem that plagues literally any mission we try to send to Mercury. You have to notice the sheer scale of the mismatch here. Mercury's weaker gravity is constantly fighting the sun's immense, overwhelming gravitational pull. When you send a probe toward Mercury, it is naturally and powerfully pulled directly into the sun. It is the ultimate cosmic trap. You aren't just aiming for Mercury, you are actively trying to avoid falling into a fiery star. So how in the world do aerospace engineers solve this? Well, it comes down to a delicate, incredibly complex Goldilocks speed balance. If the probe travels too slowly, the sun's gravity just swallows it whole. Poof, mission over. If it travels too fast, it zips right past Mercury, unable to be captured by its orbit, and we miss all the scientific data. The solution is finding that perfect speed. You basically have to fly the probe in like a high-speed race car taking a tight, curved road. You have to decelerate just enough to let Mercury grab you, fighting off the centrifugal force that wants to fling you out into deep space, while also fighting the sun's massive pull. It is a literal astronomical tightrope walk. Section 3, Mind-Bending Spacetime. But let's just say you survive that perilous flight path. The reality waiting for you on the surface is completely bizarre, because getting there is only half the madness. If you were standing on Mercury, a single day, meaning one full cycle of sunrise to the next sunrise, lasts an agonizing 176 Earth days. Imagine that for a second. The rotation is so sluggish that the sun would actually appear to rise twice a day in certain parts of the sky. You would literally celebrate your Earth birthday twice before a single Mercury day had even finished. But here is where it gets incredibly weird. Contrast that agonizingly slow day with its lightning-fast orbit around the sun. A full year on Mercury, the time it takes to do one complete lap around the sun, takes only 88 Earth days. So the crucial point is this mind-bending mathematical reality. 1 Mercury day is exactly equal to 2 Mercury years. Think about what that actually means for the environment on the ground. One side of the planet experiences a full year of absolutely scorching, blistering afternoon heat, while the other side is stuck in a full year of freezing, pitch-black night. It's a planet of just absolute extreme dualities. Now, the reason for these super slow days is a phenomenon called tidal locking. Because Mercury is so close to the sun's immense gravity tightly grips the planet, acting almost like a giant brake. It forces Mercury to drastically slow its rotation over billions of years. It's actually the exact same gravitational staring contest that Earth has with our moon, which, if you think about it, is why we only ever see one side of the moon. Okay, but what explains those incredibly fast years? For that, we have to look way back, 4.5 billion years ago, to the formation of our solar system. As the early protoplanetary disk of gas and dust was shrinking, it created a massive amount of forward momentum for the planets closest to the center. Think of it like an ice skater or a ballerina. When a ballerina pulls her arms in close to her body, she spins dramatically faster, right? Because Mercury formed so close to the center of the spinning disk, it was given this massive acceleration, whipping it around the sun at just breakneck speeds. Section 4. Future mysteries to solve. This planet is such a paradox, and honestly, we've barely scratched the surface. To crack the remaining mysteries, the Bepi-Colombo mission is currently on its way, and one of its biggest targets is Mercury's volume. Look at this. Mercury's metallic core takes up a staggering 85% of its entire volume. To put that in perspective, Earth's core is only about 20% of its volume. Mercury is essentially a giant metal cannonball flying through space. Yet, despite having this massive core, it possesses a surprisingly weak magnetic field. And strangely, that field is heavily skewed, being much stronger at the North Pole than the South. Why? We just don't know yet. And this brilliantly illustrates how the probe's advanced instruments are going to tackle these bizarre geological anomalies. Bepi-Colombo brings an incredible arsenal. It's going to map the chemical composition, dive deep into the geophysics, and, most excitingly, it's equipped with something called an Italian spring accelerometer. This hypersensitive device isn't just looking at rocks. It is designed to detect the literal curvature of space-time in the extreme high-gravity environment right next to the sun. Which leaves us with this final, thrilling thought. Because Mercury sits so deep inside the sun's gravity well, it is the perfect natural laboratory to test the absolute limits of physics. What will Bepi-Colombo finally reveal about Einstein's general theory of relativity? Could measuring the space-time curvature near the sun actually force us to rewrite our fundamental understanding of how the universe works? We'll have to wait for the data to come back to find out. But one thing is for sure. Mercury might be small, and it might be wildly hard to reach, but it holds some of the biggest secrets in the cosmos. Thanks for joining me on this explainer. Stay curious and keep learning.